So the most basic thing in programming is Boolean logic. Let's have a look at it. This is the basis of all digital programming. Let's create a new window here. If you don't understand Boolean logic, you are never going to be a scientific programmer. You're going to be an alchemist, like a cargo cult programmer. Open. Let's create a new folder in here. I'll demonstrate how it works. We'll go into workspace and create a new folder, and we'll call it Boolean Logic. Missing the C, but whatever. So this type of logic is formulated by a guy called George Boole back in the day. So I guess I'll just create a file in here called Boolean, and we'll make it a Markdown file. Okay, so Boolean logic, theoretical. Boolean logic is based on a unit called the bit, and a bit can have two values. Just two values. We call it digital. It's a digit. When we think of digits, we normally think of preview to the side. Okay. It's the fundamental atom, the fundamental particle of computing. It's the fundamental particle of computing. Okay, can have two values. No, can have one of two values. See, that's precise. It can't have two values. It can have one of two values, 0 or 1. And we can say that's off or on. And in modern computer systems, it's actually like a low voltage or a high voltage, but we call it off or on. So off or on, and if you imagine it as a switch, it could be, is there a way to draw an off and an on switch here? Yeah. So that's off or 0. If you make it as an electronic circuit, it would look like this, yeah. Or maybe you could do like this. Yeah, I could draw it like that, actually. But anyway, I'm going to draw it like this. Off and on. So the first operation, I'm going to show you three basic Boolean operators. Okay, so the first operator is called not. And what not does is it simply reverses the value of the bit. So if I say not, oh yeah, as well as 0 or 1, off or on, we also say true or false. True or false. So here this is also false, and this one is true. Not. Okay, so not reverses, make this a heading level 2. Reverses or inverts the value of the operand. So it takes a single operand. So you say like not true. We'll make these lowercase. Not true equals false. And not false equals true. So you can draw a Boolean table for the operator like this. How do you make I think there's a way to make a table. So let's make sure that this thing is actually broadcasting. Is this thing on? Dun dun dun. Is this thing on? Yes, it is. Okay, great. So yeah, the most basic thing in programming today, I'm talking about that. So I have a friend who asked me, my son is 6 years old. I'd like him to get started on programming. What's the best way to get him started? I started programming on paper. Kids today have tablets, and tablets are not production devices, they're consumption devices. So they're not, I don't think a tablet is a good device to really start programming on. It's best to start on paper. If you want to teach your kid to program, you should learn Boolean logic and understand it yourself, and then teach them that. If you don't understand Boolean logic, you're never going to be a scientific programmer. You're always going to be like an alchemist or a cargo cult programmer at best. You've got to get a good solid grounding of this very basic thing. Boolean logic. So let's go into the studio. Yeah. Let me just make sure that we're seeing the right thing in the stream. Yeah, good. So Boolean logic, it's named after a guy named George Boole. English mathematician, I think. Logician. Anyway, he formalized this logical system which can be implemented in electronic circuits. And it is the basis of all modern computers and programming. Boolean logic. So let's see, formalized by George Boole. Okay, so in Boolean logic, the fundamental particle is a bit. It's called a bit, and it can have one of two values, either 0 or 1, false or true, off or on. Technically, it's implemented in modern computer systems as a low voltage or a high voltage. But, let's just look at 0, 1, off, on, true, false. So this is kind of like a little diagram of an electronic circuit that implements it, and it's basically a switch. So you turn the switch off, it's false. You close the switch, the switch is on, that's true. So electrical current can flow through the switch when it's closed, that gives you true. When you open the switch, it gives you a value, no current coming through, no voltage, it's off. So the first operator in Boolean logic is called not. It takes a single operand and it reverses or inverts the value of the operand. So, if you have true and you go not true, that's false. If you have false and you say not false, then that's true. So I can make a table. How do you make a table in Markdown? Let me check. Markdown table. Markdown table. I'm just Googling it in another window here. Creating a table Markdown tutorial. Yeah, come on. Okay. Right, like this. Okay, so there's no opening things on it. No closing things. So, if I put that there we go. Ta-da! So, not true becomes false, and not false becomes true. Like that. Pretty easy. Another way of drawing the same table is to go 0. Actually, I should reverse these because, by convention you put 0 first. So that becomes true. And this one becomes false. That becomes 0, that becomes 1. There you go. Not. That's a pretty simple operation. It's just an inversion. A not. That seems like such a simple and obvious thing, right? Okay, if it's not false, it's true. If it's not true, it's false. Not, the not operator. Okay, so the next one that we're going to look at is OR. No, not this thing, OR. So what it does is it takes two operands. So not takes one operand. It takes two operands, we'll say A and B or X and Y. This is like a linguistic description. Returns true if one of the operands is true. And to be exactly precise, if at least one of the operands is true, returns false. Otherwise, which means if both operands are false. So actually we should modify this truth table up here. Not. So we would say here operand and output. So true becomes false and false becomes true. Yeah. Do the same thing here. Operand and output. And then we'll reverse these two. So control X that out. X, command X. There you go. Now the OR operation, so if we say operand X and operand Y, and then the result, output. Okay, it's a combination of cases here, so what? No. Okay, so if operand X is false, operand Y is false, then the output is going to be false. If, let me get this little window out of the way. Actually, I'll drag all of them out of the way. Okay, now, next case. This one is false. Close this. This one is true. Then the output will be true because at least one of them is true. Make this one true. Make this one false. And then the output will be true. If this one is true, this one is true. False, 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 true, true, false, true, true. Yeah. So there's only one case. There's only a four possible combinations. There are four possible combinations. And you can know that there are four possible combinations because each of the bits has two possible states and there are 2 bits, which means that you have 2 to the power of 2 possible combinations equals 2 times 2 equals 4. So there are 4 possible states. And then let me copy this table and I'll do it with zeros and ones. So you got 0, 0 produces 0, 0 and 1 produces 1, 1 and 0 produces 1, 1 and 1 produces 1. There you go. Or. So if you wanted to implement this as an electronic circuit, it would look something like this. You have a switch. This is your operand X here. And this is your operand Y here. And then your output comes out here. So if you look at this as a circuit, logically, you know, just thinking about it logically, this state that we're demonstrating it in here is 0 and 0, which means nothing comes out this end. 0. See, we have a 0 here, nothing comes out. I'm going to copy this whole thing. Let's look at the second case, where this operand becomes true, in which case you can see the current would flow through this branch here, and as a result you would get some output on this end. Let's do case 3. Case 3 looks like this. In which case you get some output at the end. And then case 4 looks like this. Close the switch here to make it true. And you get something out at the other end. So you can see it maps to this output table. And basically this Boolean logic here has now been implemented as these electrical switches, and you can see that the circuit behaves according to this Boolean logic table here. Okay, they didn't come out very well in the Markdown, so I've got to do this to them. Ta-da! Oh yeah, I can just do the whole thing. So demonstration using an electrical circuit. An electrical circuit with 2 switches. This NOT one, I don't know how you'd implement that as an electrical circuit. You might have to use some kind of component in it, like a capacitor, or how would you implement this as an electrical circuit? Let me just think about it logically. If I open the switch, the output goes low, drops to 0. If I close the switch, yeah, I don't know. It's the kind of thing you could Google, how to implement that as an electrical circuit. It probably needs a component other than a switch in it to make it happen. Okay, next logical operator is called AND. Takes 2 operands. Let me just use the same language, X and Y, okay. X and Y returns true if both X and Y are true. Otherwise returns false. So I can just copy my OR table and drop it in here. False, false, false. So this one will be false. They both need to be true. False, false, and then only in one case. So if you have a look at the OR table, in all cases except for one case, it returns true. The only time it returns false is if they're both false. That's OR. With AND, it returns true in all cases except when they're all false. So they actually overlap here. Hang on, this is not correct. This should be 0, and this is 0. Yeah. So there is an overlap between the two, like OR and AND will both return false, OR and AND will both return true, and where they differ is in this middle section. Here's how we implement as an electrical circuit. Like this. So we need to have two switches in this thing because it's got two operands. Yeah. And again, if you don't understand this, you're never going to be able to actually really program. You're just going to be like a cargo cultist, just like kind of randomly doing things to see what happens without understanding them. Okay, so here's our electrical circuit. Now that's obviously going to return... but no, it's not an OR circuit. So that's the OR circuit, right? In an AND circuit, it's much easier to implement than an OR circuit. This OR circuit is a parallel. So these two branches are in parallel. Basically what happens in the case of the AND circuit is that these two switches are in series. So if you think about that, I mean, in order to get anything out the end here, you basically just have to close both of the switches, right? Anything else is going to return a 0. You know, like, so we got 0, yep, and then 0 and 1, so we just close this switch, but still nothing is going to come out. For this one, we close the first switch. You're still going to get nothing. You're only going to get something out like that. So that's an AND circuit. That's pretty easy. The OR circuit would have actually looked better if I'd done this. There we go. And then I think if I just replace these like this, that might look a bit better. Like that? Yeah. I think so. 5. Okay, that's a bit weird. And then 4 on this side. Yeah. Four on this side. There you go. That looks a bit better. Okay. It's basically... So I'll add that as a note. It is a parallel circuit. It's a circuit. It's a circuit with two. It's a circuit with two switches in parallel. They're not two parallel switches. They're two switches in parallel. Okay, so it is a circuit with two switches in series. Okay, so application. I'll do another one a bit later where I show you how you combine these three basic circuits to get more advanced operations like NAND and XOR. Okay, so in programming, it's something like, let's imagine that we'll do not first, right? Actually, not is a little bit more advanced. So first, in its application and usage. So first we'll do OR. Okay. It's basically like an instruction that should be executed if one or more conditions are true. For example, turn on the kettle, it's like for boiling water, jug, if it is 8 a.m. in the morning, or a motion detector senses that I got out of bed. So what that will do is, it means that the kettle will automatically turn on at 8 a.m. in the morning, or, you know, if I get up at like 6 a.m., it'll turn on then. But if I'm still in bed at 8 a.m., the kettle's going to turn on anyway. So here you say if time is 8 a.m. or motion detected, then turn on kettle. And so what happens if I'm away on holiday? I'm not even in the house. In that case, you say, turn on this kettle at 8 a.m. and motion detected. That's going to deal with the case where I'm away on holiday, and so there's no point turning the kettle on. Maybe you want to make it even, it's like, what happens if there's not enough water in the kettle? So if the time is 8 a.m. and motion detected, and so you've got a sensor, kettle has water. So there's a sensor inside the kettle that tells you that it has enough water in it. Like that. Then you can combine them, right? So combine the circuits. Combination. So we can say if time is 8 a.m. or motion detected and kettle has water. Then turn on the kettle. And you see how I use these parentheses to group them? There is operator precedence, like, you know, BODMAS, I think it is, brackets over division, multiplication, addition, subtraction, something like that. And so this circuit would look like this. So one of these two conditions is true. This one here is time is 8 a.m. This one here is the motion detector. So I have to be home. No. Either it's 8 a.m. or the motion detector fires, in which case the next thing that will happen in this circuit is it's going to check to see if the kettle has got water in it. And then you get either the kettle turning on or not. That's how you implement that as an electrical circuit. Does this work better like that? Yeah, I think so. So an instruction should be executed if both conditions are true. For example, only turn on the kettle when it is 8 a.m. and the motion detector senses that I'm at home and awake. You can chain more together conditions. For example, only turn on the kettle when it's 8 a.m. and the motion detector senses that I'm at home and awake, and the kettle has got water in it. You can combine different operators. For example, turn on the kettle when it's either 8 a.m. or the motion detector senses that I'm awake and the kettle has water in it. So there you go, Boolean logic, this basic logical operators and these truth tables, electrical circuits that implement them, and then what that looks like in programming. This is a source of bugs in programs where these conditions are not, they don't properly overlap, and you design these electrical circuits that virtual electrical circuits that fire and cause effects to happen when they shouldn't have. So it can get quite subtle because you're basically building these kind of they're kind of like virtual electrical circuits that do stuff in this other virtual world that cause more virtual effects. And let's see if I can do not. Let me just think through some different scenarios and see if I can generate one with a not in it. So I'm not at home. It's 8 a.m. Yeah, I could say don't turn it on at... If we have a look at these earlier conditions, basically this first one here, I'm saying if I get up at 5 a.m., it's going to turn the kettle on. So another way that I can do it is like this. Turn the kettle on. It's 5 and motion and 8. So no, we got that one there. Okay, well, let's say this. So turn the stereo on at 8 a.m. if I'm still in bed. That will do it. So to do that, you'd construct something like this. Okay, if time is 8 a.m. and not motion detected, then turn on stereo. So it's kind of like an alarm, basically, that only triggers if you haven't got up. Now, of course, you'd have to build a latch for the motion detector Because what happens if I get up at 6 a.m., 4 a.m., whatever, do my thing, and then I'm sitting down at my desk at 8, and now the motion detector is not detecting any motion. Now the stereo will turn on. So you'd make like a trigger, you know, that would have like a time range, and it would trigger at 6 a.m., let's say. The motion detector triggers, okay, he's up, and then it stays triggered for a period of time, and then it wipes itself after some time. That's called a latch in an electrical circuit. And so you build a virtual latch in code for that kind of thing. I'll just build one using pseudocode here. So I'd say I create this thing called a motion latch, right? Motion sensor with latch. So this is just pseudocode. It's not any actual syntax of a programming language, but I just do this. So it needs to have a timer. So first I probably have to build a timer. Well, I have to have a clock, right, which just gives me an absolute time. Get time. And then I have to have a timer, which is this timer, I need to tell it set duration. And then after I set the duration, it will return. And so that set duration should take a duration of time and an action like that. Get time. So motion sensor with latch. So this motion sensor can trigger on motion. And it just takes an action. Okay, let's try this. So I get my motion sensor with latch. Call it that. Trigger on motion. And then the action I want it to perform is I won't think through too many cases, I'll just do it. So then I want to do a timer. Set duration. And then duration. Let's say 1 hour. So it's only going to trigger once an hour. I guess motion detected. Okay, yeah, this is actually an edge and a level trigger. So in an electrical circuit, you have an edge trigger, which looks like this. It's a level trigger. This is an edge trigger here. It's not necessarily the trigger, but you could have something like this. It just emits motion detected events. Motion detected. This is like an event emitter. Something happened, something happened, something happened, something happened. But you see, the thing is that with my time as 8 a.m., unless the motion detector triggers exactly at 8 a.m., it's always going to be like, no, there's no motion detected. But it's kind of like, this is like a motion detector that just triggers whenever it sees motion. But what we want to do is we want to design a motion detector in software that effectively does something like this, that we get motion detected here. It's funny, why is that there? So we get the motion here. And then it stays motion was detected. And then it returns back to here, no motion. Actually, the easiest way to do this, more simple than this, would be for this thing to have last motion. So it doesn't even need to have a latch in it. It just needs to have a memory of when the last motion detection was. Yeah. Last motion detected, so I don't even need to have this timer. It makes it a lot easier. It's better than a latch. And so what I can do now is so here this only works if the motion detector fires exactly. AM. If I am at my desk and the motion detector doesn't pick me up, the stereo will turn on, which is not what I want. Okay, so in that case, what I want to do is this. So I'll say if time is 8 AM and motion detector, a motion sensor dot last motion detected. Don't worry about that. And then we'll just use it as like this. It was yesterday. But what happens if I go to bed at 2 AM? Or 1 AM? So, just do more than 4 hours ago. Turn on the stereo. 4 hours is not enough time to sleep. So we can say greater than 4 hours ago. And actually, it would be time since. Like this. That's the implementation. So anyway, this gives you an idea of like how this Boolean logic relates to programming. Boolean logic, yo. I'll have a look at XOR and NAND in my next stream on this series, on this subject.